systems, many of which use the combustion of fuel. We also have a new generation of electric propulsion, which still has a long way to go to be deployed in mass, but small aircraft and other specially equipped airplanes are using it right now. Do you know that a glider can fly without an engine? To learn more, watch my video about gliders on the top right corner. Let's start with the most common type of engine, the piston engine. It's the same type of engine used in cars. The piston engine is very reliable and has been used in airplanes from the beginning of aviation. Pistons can be arranged in many ways, and you can have as many as you can fit under the engine cowling. They can be inline, opposed, V-type, or radial. The more cylinders you have, the more power output you'll get, but also more fuel consumption. If you don't know how an engine works, I'll show you real quick with this animation. Normally, we'll find 4-stroke engines in airplanes. This means that the cycle has 4 stages to complete. The mixture of fuel and air goes into the cylinder, and then the intake valve closes. The piston goes up and compresses this mixture. That's the compression stage. From there, the spark plug ignites the mixture, and the combustion generates a small explosion that pushes the piston down. That is the combustion stage, where the power is generated. The last stage is the exhaust, in which the exhaust valve opens and the residual gases exits the cylinder. Then the process repeats. In cars, you'll normally see cylinders arranged in line or in V, but in airplanes we can also have other arrangements including opposed and radial. The main difference with these arrangements is the cooling and aerodynamics. See how a radial engine is exposing all the cylinders directly to the airflow. Thus, it doesn't need an extra coolant system since it will be cooled by the air. But this arrangement will produce a lot of air drag, slowing the plane down during its flight. Many early airplanes used this kind of engines to simplify the cooling problem. The other kind of arrangements, especially the V-type, will allow for a slimmer design and better aerodynamics. But the cooling will be more critical, relying on more complex cooling systems, but totally worth it if you want to get the maximum speed out of the engine. To go faster, a piston engine won't do. You need a better technology. For that, we can use rocket engines, but they're very inefficient and they burn fuel very quickly. Jet engines or turbines came along and they were the answer to the speed and power problem. After many years of development, they were ready to be deployed, first being used in the Second World War. But after the war ended, the technology kept improving to the point it was very efficient, reliable, and perfect for its use in many variants of engine types and aircraft. The turbine uses a lot of small blades rotating at high speed. The engine takes air from one end and forces it through the different stages where it is compressed, then mixed with atomized fuel, then ignited. Then the expansion of the gases will escape towards the back, forcing the rotation of the next set of blades in the turbine, which at the same time turns the whole system. Notice the similarity on the 4-stroke engine cycle. In the turbojet engine, we have the air intake, the compression, the combustion, and the exhaust stages. But this is happening continuously, not like a cylinder where every stage is defined by the stroke of the piston and then the explosion is the combustion. Nowadays there are many types of jet engines. There are turbofan, turbojet, turboprop, turboshaft, and ramjet engines. The most used in civil aviation is the turbofan engine. In this type of engine, there is a large fan at the front that sucks all the air in, most of which is used to generate thrust, and only a small percentage actually goes into the combustion stage. The advantage of this kind of engine is that it's a lot quieter and more efficient for subsonic speeds. The turbojet engine is the one that we saw in the first example, and all the air that gets in is used for the combustion process. It's very powerful, very noisy, but somewhat smaller than the turbofan engine. The turboprop engine uses the power from the turbine, and through a gearbox the rotation is transmitted to the propeller. Compared to turbofans, turboprops are most efficient at flight speeds below 725 km per hour or 450 miles per hour, because the jet velocity of the propeller and the exhaust is relatively low. Modern turboprop airliners operate at nearly the same speed as small regional jet airliners but burn 33% less fuel per passenger. However, compared to a turbojet, which can fly at high altitude for enhanced speed and fuel efficiency, a propeller aircraft has a lower ceiling. And compared to piston engines, their greater power-to-weight ratio, which allows for shorter takeoffs and reliability, can offset their higher initial cost, maintenance, and fuel consumption. Also, as jet fuel can be easier to obtain than aviation gasoline in remote areas, turboprop-powered aircraft like the Cessna Caravan and Quest Kodiak are used as bush planes. The turboshaft engine is similar to the turboprop, but it is connected to a big shaft and it's normally used for helicopters. The workings of the whole system is practically the same. It can also be used for military tanks and even boats. Lastly, we have the ramjet engines. These engines are more like a rocket, with the difference that they can only produce thrust once they have a fast airflow to start working. In other words, the airplanes have to be flying already at a fast speed for this engine to work. This engine does not have a set of blades like the turbines. It has very few moving parts, and it relies on its shape to slow down the supersonic airflow at the intake to a subsonic speed, driving the air to a compression stage and then burning the fuel with this compressed air to generate supersonic thrust towards the nozzle. This engine is used in the SR-71 Blackbird. Although you might wonder then how can this airplane take off if the ramjet engine can only work at a supersonic speed? Well, this airplane has a turbojet engine nested inside the ramjet. It's a two-in-one solution. Once the plane reaches the speed needed, then there is a bypass that will allow the engine to work mostly as a ramjet engine. It's a bit more complicated than that, so I suggest you watch the videos from other YouTube channels, which links I provided in the description below, to have a more detailed and better understanding on how the engine works on the SR-71 Blackbird. I could keep talking about other types of propulsion systems for aircraft, like the new electric motors, in which the only limitation we have now is the amount of energy we can store in our current battery technology. But it promises a great future for electric aviation. But I think this deserves an entire video on its own. I will only mention a few weird propulsion systems that are not practical or not developed enough to be used in aircraft. Going back in time, we have a steam-propelled aircraft. One of the most successful was the Bessler biplane, but this steam engine was heavier, less efficient, and more complex than a conventional internal combustion engine. It could not compete with the combustion engines, so it was never put into production. Human-powered aircraft is another peculiar type of propulsion, but it's completely possible, only in good weather conditions and if the person is not hired. Then we have rocket propulsion, to go at the fastest speed possible, but for a brief moment. And the final one I'm going to mention is the ion propulsion, a very new technology. And that's it for this video. If there's another type of engine you would have liked me to mention, just leave it in the comments below. And I hope you enjoyed this video. Thanks for watching, and I'll see you next time.